Okay, shall we start, Klaus?
Yeah, I'm ready.
Good. Hello, everyone. Welcome to the last lecture of the summer school. I hope you enjoyed so far, and I hope you had a very nice evening yesterday. Today, it's 27 degrees outside. It's not something very typical in Denmark. So I feel a bit bad that I'm now standing between you and good weather outside. Maybe you plan to go beach, whatever. So, yeah. But I hope this lecture will be good enough that you stay your time here rather than going outside. Well, yeah, today we are going to talk about market design for integrated energy systems. Maybe so far in this summer school, we haven't talked much about market design. So I hope it could be something for you and you can learn something out of that. You are going to have 3 parts this lecture. Part 1 is about preliminaries. It will be a short one just to make sure that we have the same understanding about the status quo of markets, especially electricity markets in Europe, US, and the rest of the world. And then the part 2 will be about the basics of market design. So I know some of you already, you took my online PhD course, so you may see some familiar slides. So I hope the second part will not be very boring for you. And the third part, we will see how far we can go, but we will focus on integrated energy systems and how market should be designed for integrated energy systems. You can think of power systems coupled with district heating or natural gas or hydrogen systems or transportation. Okay? Good. So the first part is preliminaries. I'll try to have a very interactive lecture with you. So I may ask a bit more than usual questions. So let's have fast, short, to the point answers, right? To be able to move forward with the talk. Good. So first about the preliminaries. From market to operation. Let's see how electricity markets they are working. First, with a focus on Europe, and then we will talk about how electricity markets they are working in the US and in the rest of the world. So if you have this time axis, so the first markets, okay, here I'm not talking about futures markets, I'm not talking about forward contracts, I'm not talking about capacity markets. So I just start with the day-ahead market. The focus is that. So first, for example, in the Nord Pool, in the Nordic countries, we clear day-ahead market, right, at noon, at 12 for the 24 hours of the next day. This is how it works in Europe, right? And then you have intraday market. Do you know how is the intraday market in Europe, or at least in Nord Pool? Have you heard of that? When is the time period for solving for clearing intraday market? So at 12 we start clearing day-ahead market. At 2 p.m. of t-1, the market outcomes are disseminated. So everyone knows their schedules, and everyone knows the market prices. So from 2 p.m. onwards until the next day, we have intraday market. When do we solve it? When do we clear it? For us? Continuously. So intraday market in Europe is continuous. What does it mean?
That means you can match and buy and sell it in.
Okay. So exactly. So what happens in day-ahead market is that Nord Pool or Apex or anyone, they are collecting bids from demand side, from generation side, and then we have a closure for the day-ahead market. Then we clear the market. The objective is maximizing social welfare, right? So it's a uniform pricing. But in continuous market, we don't have a specific time for clearing the market. It's continuous. So what does it mean? For example, Nick says that I need 1 megawatt extra for that specific hour, right? And then Florent here says that, yeah, I need 1 megawatt demand. So as a Nord Pool, I match you. if your prices are matching. For example, what Flora is willing to pay is at least as much as Nick is willing to sell. So it's online matching. And then we are using pay-as-we schemes for that. Okay? And here in Nord Pool, intraday market continues until 1 hour before the real time, H minus 1. And in intraday market, you can update your schedule. But this day ahead and intraday markets are being done by Nord Pool. So now in Nordic countries, we have also other market operators like Apex. They can come. So as supply or demand in Nordic countries or in England, you have option to go and trade in Apex or Nord Pool. How is it possible? So if we have two market operators, both of them they are clearing day-ahead market or intraday market, what does it mean? Do we have different prices? For example, next day? So how is that?
They have the same algorithm.
Yes. They are both collecting the bits, and at the end of the day, the market should be cleared exactly the same way as prescribed by Euphemia. That's the algorithm in Europe. Okay, so when you are done with day-ahead and intraday market, what's the next market? Real time. So in Europe, it's not market operator anymore, but it's the transmission system operator, TSO, who clears the rest of the market. So we go for balancing markets. And in Denmark, it's Pinakine, our TSO, who clears the balancing market. Who is the TSO in Finland? Fingrid. In Norway, it's not net. In Sweden, Svenska Kraftnät. In Germany, we have 4 TSOs. In Netherlands, 10. Okay, you know, good. So the TSO clears the balancing market very pretty close to real time to make sure that we have instantaneous, constant balance between power and demand, right? So for that, the TSO needs to activate some generators if needed. But for that, we need to already book some generators, some resources to make sure that if we need that in the real time, we can activate that. So for that, TSO does what? Reserves capacity. Let's say ancillary services. In Europe, it happens separately than day-ahead market, a time period before day-ahead market. What ancillary service markets we have, I'll talk about that later. So far it's clear? Right. So you have the same understanding? Nice. So here we have audience from US, from Europe, from Australia. So can you tell me how these different markets, conceptually, fundamentally they are different? Let's first focus on US versus European markets. So for example, US markets, PJM, New England, ERCOT, I don't know, Kaizo. So these markets, how are different than European markets? Yes?
The pricing is LMP based?
Where? Where? In
All of the...
US or Europe?
In US.
In US it's LMP based. So what, but in Europe?
It's not.
It's not. So what's that?
I don't know.
Okay.
What the word is.
So zonal. Very good. Can you tell what zonal means?
So zonal means you approximate the topology of the grid by having a big zone.
Okay. I'll tell about that. So far, okay. In Europe, we have zonal setup. In US, we have nodal setup. What's that? I'll talk about that. Any other difference?
About the bidding principle?
Pardon me?
Bidding.
Bidding. So how different are they? Well, if you like work on market design, you have to have that, right? Because we have to make sure that the methodologies we develop in our thesis, as much as possible, they should be practical and they should be, in the same way as the industry works, or not way different than that. to make sure that we are going to have impact, right? So that's why I'm asking all these things. So you said about bidding. So how bidding is different in Europe and US?
Europe we provide real bids. In US we provide production characteristics.
Okay. Kinda. Any other point? Yeah, Thomas?
I think the philosophy is different. In Europe, it's mostly like a financial market. Anybody just sells a quantity price bid. In US, it's more of a potential optimization.
Okay. Very good. I'll talk about that. Any other difference?
Who operates it also?
Oh, very good. Who operates the markets in US and Europe?
In Europe, there's like different instances, FX for example, and all TSOs.
Okay.
In the US, like market and system operators.
Okay.
All in all.
Yeah? Very good. Nick? Any addition?
In Europe,
I'm not
Yeah, okay. I'll get back to you, Yannick.
I'm not sure what was mentioned, but in the US, the real-time market is sort of the spot market,
Okay?
whereas day-ahead market is used to hedge your decisions.
Okay.
Whereas in Europe, the day-ahead market is more
Okay.
like the central spot market.
Very good. Yannick?
in Europe we have energy-only markets, while
Yeah.
in the US we have additional out-of-market payments like uplift.
Yeah, very good. Uplift, very nice. Good. Okay, let me try to summarize. First of all, in Europe we have different entities for clearing markets. The day-ahead market, intraday market, they are being cleared by market operator like Nord Pool, like IPEX. And then balancing markets and ancillary service market, they are being cleared by who? By TSO. But in US, all markets are being cleared by one entity, which is Independent System Operator, ISO. So in US, we don't have a separation between market operator and TSO. That's very fundamental. Okay? Then, as Farad said, we have zonal setup in Europe. So we have, 20-something zones, bidding zones in Europe. So for example, how many zones do we have in Denmark? Two. DK1, DK2. How many zones do we have in Finland?
One.
In Germany? One. In Sweden? 4 bidding zones. How many bidding zones do we have in Norway? 5. Very good. So what does it mean? So if Germany, the whole Germany is one single node, one single zone, what does it mean?
Everyone pays the same.
Everyone, the price, the zonal price in the day-ahead stage for the entire Germany is the same. Why? Because we exclude what? Transmission constraints. So in the day-ahead stage and in the intraday stage, they exclude transmission constraints within the zones. The only constraints we impose are big field zone constraints that we call them ATC constraints or NTC, net available NTC, net transmission capacity, or ATC, available transfer capacity constraints, right? And who are setting those constraints? TSOs. Good. Very good. While in US, we have nodal setup. So it means that the market price here might be different than, a neighborhood city. Very good. I hope I covered everything here. So I said that we are excluding internal transmission constraints within the zones. Is it exactly the case in Europe, or we are improving?
No, it's improving.
Pardon me, Brittany?
It's changing.
It's changing. How?
Well, there's like NTCs, and then they're moving away from that to more like advanced methods.
So in Central Western Europe, including Germany and neighboring countries, so we moved beyond ATC constraints. So somehow we try to represent the internal zonal transmission constraints within the zones. Through which method? Flow-based method. Flow-based method. And it's going to happen in also Nord Pool, in Nordic countries, starting from January, the coming January. Okay? Good. In Europe, we since the ISO and TSO, market operator and TSO, they are separate entities. So the market operator clears energy market day ahead, while TSO clears the ancillary service capacity market. They are separate markets. So in case of Nord Pool, at least in Denmark, first we have ancillary service capacity market, and then it's the energy market. While in the US, we have one operator, one system operator, ISO. So we have a joint market clearing for energy and reserve. That's a very fundamental difference. Okay? Which one is more optimal? Not more. Which one optimal? Which one is suboptimal?
Depends.
US is optimal.
In that case, US is optimal because you make decisions at the same time. Good. Some of you also mentioned about bidding. So always we say that in Europe we have complex bids, simple market clearing. What does it mean? In US, the first problem we solve when we clear the market, what's that? Unit commitment. What type of unit commitment? Security constraint unit commitment. So you have what? So what type of optimization problem it is? Mixed integer linear programming. Yeah. So you have binaries. So if you have binaries, what kind of problems you have?
Challenging.
You cannot drive dual variables. So you cannot drive prices as it is. So what we do in the US? Come on. So how we end up to uplift payment? First we solve mixed integer linear program. Then what we do, Farhan? We fix binaries. Then we end up in a linear program. Now in linear program we can drive dual variables, which are our prices. Is it fun or do we have challenge? Do we have challenge? Farhan, why do we have challenge?
Cost recovery is not always guaranteed.
Sorry?
Cost recovery is not guaranteed.
Why? Why cost recovery is not guaranteed?
The deal doesn't reflect the startup cost.
Exactly. If you have fixed cost, if you have a startup cost, when you fix binaries, they will be gone. So your dual variable will not see those costs because they are going to fix costs. So some generators with high fixed costs, with high startup costs, they will lose. So you need some payments outside the market that we call it uplift. And in US, so we have security constraint unit commitment. So ISO clears the market, including everything, all constraints, whatever. So you send as a generator, as a demand, you share all your constraints, all your costs, whatever, and then it's the ISO who clears, who solves a complicated optimization problem, right? So it's simple bits, complex process. In Europe, it's exactly opposite. How?
Bidding is a lot more complicated.
Why?
You have to different times constraint. You can say ramping limits. You can sustain your ability for the next 10 steps.
Okay, let me reword my question. In market operators in Europe, do they care about your internal unit commitment constraints? They don't.
It's considered repeating.
The market operator says, it's your problem. I don't care what kind of constraints, technical constraints you have. So that's why generators demand they have to internalize their internal constraints. So, generator, let's say you have a generation capacity in Europe. How can you make sure that your bidding, your bids, understands or includes or embodies the constraints you have, like minimum uptime, minimum downtime, ramping constraints? How to make sure? Because market operator will not care about your constraints. So what do you do?
There are different types of bids.
There are different types of bids. Very
Except for given number of hours.
very good. There are very more complicated type of bids in Europe. In US, you have just price, quantity, bids, simple. I'm gonna produce 10 megawatt at price this done. In Europe, we have something called block orders. Block orders. So what does it mean?
Bidding of blocks.
Yeah. For example, you can bid something like, say, This is time, this is quantity. You can say as a generator, this is my bit. And the average price is $10 per megawatt hour. So as a market operator, either accept all of that or nothing. All or nothing. So why do you do that? Because you, as a generator, as a portfolio of generators, as a producer, if you have a portfolio of generation assets, you try to internalize your constraints, right? And this is one way. So even if you have more complicated, more funny, I would say, block orders in Europe that I'm not gonna cover that. So in Europe, we have this kind of block orders. So this is the orders. Also, you can submit price quantity bits to market operators in Europe. And then the market operator collects the bits. And what kind of optimization problem the market operator is solving in Europe? Is it linear program or something else? Do we have binary in European electricity markets? We don't have Untitled constraints. So is it LP? It's MILP. So what's the binary? All right? Block. Either accept the whole block or not. That's a binary decision. So still we solve MILP. Mixed integer linear program in Europe. Is it possible that we may have missing money, like the same way that we have in the US, if we fix binaries in Europe?
No.
Yes. Do we pay uplift in European markets? No. So a generator may end up in a negative profit. So what do we do? That's generator's problem, right? We kick out that bit. So it's paradoxically a rejected bit. It's good for social welfare, but since it doesn't guarantee the non-negative profit for that generator, we kick that bit out and we clear the market again without that bit, right? Okay. So some fundamentals about how markets are different. Ancillary services. Later, I'm going to talk in part 3 a lot about flexibility, right? And flexibility is all about, okay, I will distinguish ancillary services and flexibility, but that's why I focus on ancillary services also a bit here in the next 10 minutes, because we are going to talk about flexibility a lot. So I said that who is clearing ancillary service markets, I said, in Europe? TSO, not Nord Pool, not market operators. So for example, this is the balancing stage in Denmark that I captured from Energinet website. So when we say ancillary services, what kind of ancillary services we have? So for what purposes do we have ancillary services? What type of services? Pardon me? Frequency-related ancillary services, exactly. Do we have only one type of ancillary services supporting frequency? We have 3. So what are they, Nick? Okay, primary, secondary, tertiary. Okay, very good. So then what type of else, what type of ancillary services else do we have? Okay, those services supporting voltage and others? Yeah, okay. And else? Black start, yes. Open up, but you were talking about other things yesterday. What was that?
Flexibility, ramping products, for instance.
Yeah, no, one more extra type of ancillary services that we need more by getting more and more wind and phasing out conventionals. Inertia. We need inertia. We need to have inertia markets. All of them, they are ancillary service markets, right? Very good. So we talked about frequency, voltage-related services, and black start. So I gotta only talk about frequency-related service. When we talk about flexibility services, is it the same as ancillary services or no? They could be different. Pardon me?
Flexibility is a way to provide ancillary services.
Yeah, ancillary service is a way. Ancillary services is one way of producing flexibility, right? But flexibility is a very broader term than that. But maybe in this lecture, sometimes I use it interchangeably. Good. Okay, maybe you saw this picture a lot, here and there. Let's only focus on frequency-related services. Many of you, I saw that in your posters. You work on local energy markets, energy communities, collecting demand. So So why do we do that? At the end of the day, we try to collect them and make them flexibility services and sell them to the TSO, right? Otherwise, there is no reason to working on demand response, working on local energy system, working on energy communities. The whole purpose, not the only purpose, but one of the big reasons is to capture, is to collect them and produce flexibility services that we need. Okay, so we are going to produce flexibility services. The big client, not the only one, but the big client of flexibility services is TSOs. And TSO needs frequency-related services. What kind of services? Nick said primary, secondary, tertiary. So I'm going to talk a bit in the European context, right? So let's say that here a disturbance happens and frequency drops. What do you do as a TSO? You start with the primary reserve, right? And in Europe we call it FCR, Frequency Containment Reserve. Very good. And it should be activated in 30 seconds to 15 minutes. So it might be but different country by country. So FCR is our first tool, is our first, how to say, product in our defending system to restore frequency, right? Or in US, you mostly call it primary reserve. Then it's AFRR, Automatic Frequency Restoration Reserve, right? It's slowest than FCR, but it's in the second line of our defending system against dropping frequency, right? And the third one is MFRR, which is way slower than FCR and AFRR, right? So all of them, they are helping you to restore frequency. But what made them different? Their speed. How fast they are to be activated when, to be start working when we activate them. So FCR is super, super fast, right? While for MFRR, you activate them, after 30 minutes, they start being working. Clear? So which one is more pricey, you can imagine? FCR. You can imagine in FCR market, the prices are higher. MFRR have a lower price. You can go on Energenet website and check the prices. In terms of volume, the volume, the amount, the quantity that you trade in those markets. We have FCR market, AFRR, not necessarily markets yet, they are bilateral mostly. MFRR, we have markets. So in terms of quantity, which one has more quantity?
By volume, you mean energy or?
Yeah, energy, the capacity also.
AFRR.
MFRR has way more capacity to trade. Good. Oops. Okay, so we talked about different markets. Let me check the time. This should be a preliminary talk. Okay, something specific about ancillary services in Denmark. We have two zones in Denmark, DK1, DK2. DK1 is Jutland, the other side of Denmark. Here we are in DK2. And apparently, we have different types of ancillary services in DK1 and DK2. In DK2, we have more type of ancillary services. Any idea why? Pardon me?
It's less robust system.
They are connected, right? So why? The whole European system is connected. They are not? They are not synchronous. They are connected, not necessarily synchronous. What does it mean? Okay, DK2, which is here, it's connected to where? To Nordic system. It's a smaller system, and it's less stable. So you need more type of frequency ancillary services. While DK1 is connected to continental Europe, and you can imagine it's more stable. And yeah, Mark?
Why it's not synchronized actually with SOE?
You can go and ask. Why do we have 5 zones in Norway? Why do we have 4 zones in Sweden?
But isn't it the logical one to be a part of?
There is no logic. There's more historical reasons how it has been developed. Right? Some questions, they don't have answer, to be honest. It's how it is. Okay, so in DK2 we have FFR, fast frequency response. It's even faster than FCR. Also in UK we have that. It's a very valuable product. Then we have FCRD and FCRN, separate markets we have in DK2. In DK1 we only have FCR. In Belgium you have only FCR, right? And then AFRR and MFRR, they are the common products in both zones. So Energinet actually is running two types of markets. Some markets in DK2, some ancillary service markets in DK1. And that makes Energinet is a very special TSO in Europe. Good. You heard about market coupling in Europe, right? So we have common day-ahead market in Europe. Is it happening for ancillary services as well? Have you heard of that? No? Yes? So what's happening in Europe?
There are some incentives to build common also ancillary service markets.
Why do we like to have a common ancillary service market? The same for the whole Europe, pan-European markets. Why?
Frequencies is unique.
Pardon me?
The frequency is unique. If you have the same frequency products, you can sell between countries.
It's way more than electricity. Why do you like to merge markets? To have better allocation of resources. Imagine, for example, in Denmark you need, I don't know, some ancillary services, and in Germany we have it. It's cheaper, but since they are not in the same market, we don't have access to them. So let's have a joint bigger market for better resource allocation, right? And that's what's happening. In day-ahead market, it happened in Europe. Now for balancing services, for flexible ancillary services, it's happening. So now we are going to have Picasso market. It's for exchange platform for AFRRs. And then also we are going to have Mari market. It's a shared market, pan-European market for MFRRs. So some stuff is happening. So a few months ago, the Nordic countries, including Denmark, they started shared ancillary service markets called Nordic Balancing Model, NBM. And then the next stage is to join Mari and Picasso. Okay? Good. So BSP, BRP, do you know what they are? They are very common words in European markets. What they are?
The one who provides balancing service, matching demand and generation.
BSP, exactly, is the flexibility provider, balancing service provider. It could be a generator, it could be an aggregator, it could be energy community, it could be anything. Right? It could be supermarkets that you control their refrigerators, whatever. But who is the BRP, Balancing Responsible Party? Pardon me?
Every market participant.
No.
Either by themselves or through somebody else.
Ah, okay. Elaborate on that.
You can give somebody else your balancing responsibility to.
Exactly. If you have a production asset, can you go and directly participate in markets? No. You have to have one, what? BRP. So you can participate in European markets through a BRP. Who is BRP?
They are usually financial.
They are financial entities or whatever, and they support you. They take your responsibility financially. So if something happens, market operators, they know, they recognize BRP. So BRPs are responsible for any imbalance, right? And, sorry, Farhad, as a generator, shall I go and find a BRP or can I be a BRP as well? You can be a BRP as well, okay? Some assets, some generators, some energy communities, whatever, some aggregators, they prefer to be BRP as well at the same time. Some prefer to be not, right? And at the end of the day, the one who is going and participating in the market, it's BRP, either with or without physical assets. Yeah?
You need to have a certain volume to be a BRP?
Yeah. No, certain budget. You could be fully financial player. You need to show that you have a good financial background to be able to buy. But in Denmark, okay, Peter is not here. I don't remember, we have 50 something, a big list, a long list of BRPs. Yeah, Fred?
Does the BRP, I'm just trying to relate it to the balancing authorities in the UK, does the BRP have to have a specific area or zone they're responsible for balancing, or?
I'm not sure. To be honest, I'm not sure. Maybe. I don't know. That I don't know. It's a very specific question. Okay, now for that you asked question, I totally forgot. We talked about European markets, US markets. How is the Australian markets or market in New Zealand or in Singapore? Is it fundamentally different? Farad, wait. Anyone else? Do we know how Australian markets it's being developed? Aquilas?
Isn't the Australian market suspended now?
Yeah, okay. My question was not in that direction. But yeah, that's something that recently happened. Yeah, my Twitter is now fully full of, what's happening in Australia. But what is the big difference in Australia compared to others? No day-ahead market. By steel generators, they have to submit their schedules or whatever. But the only market we are clearing is, real. What's the frequency of solving, the granularity? 5 minutes. Every 5 minutes, we clear a market, right? Am I right, Farad? You are consultant for them, so you have to talk about that. So what's happening in Australia as a consultant? Why it's crashing? Why are you here?
That's why I'm here.
Yeah. But, so there's no day-ahead market in Australia. Do you think that's the trend, general trend in all over the world? Do we need day-ahead market? That's a very fantastic PhD thesis project. Do we need day-ahead market? Do we need? Our quotient team says yes, right? In 20 years, do we need day-ahead market?
Because of the renewable energy, sorry, we need to move closer to real time.
Yeah, but do we need day-ahead?
In this time, I think yes.
At the moment, yeah, we have day-ahead market. But what are the reasons that we have day-ahead market historically?
Does it just have to do with the unit commitment, slow start,
Yeah.
big generators?
We used to have coal generators, nuclear generators, whatever, and we need to schedule them way in advance that they know what they are going to do next day because they were very slow. But now we are kicking them out. In 20 years, maybe we will have 100% renewable-based markets. Do we still need day-ahead markets? Maybe not. Maybe the way that Australian market will crash now, maybe that's the correct way. Maybe we don't need the markets at all. But do we need, forward contracts? Or shall we put everything in the real time? Any financial reasons? Hedging. I'm not talking about capacity markets, just energy. But do we need to have, is there any financial reasons to have forward markets? Not necessarily day ahead, maybe months ahead.
With future prices?
Why do we that? Okay, risk is one reason.
You can
But in terms of market power, do we like to have forward markets or not? Okay, there's a very famous paper, prove that we need that. You know which paper I'm talking about. Allah's Villa. It's a very famous paper, Allah's Villa paper. Google it, Allah's Villa. And they proved in 1991 why we need financial markets or forward contracts in terms of market power. But it doesn't need to be necessarily day ahead, right? Good. The definition of BRP in an AGNet website, we can go and check it out. Okay, aggregator. What is aggregator? I mean, the half of the posters downstairs, it's about energy communities or about demand response. Flora, you talked about demand response to us. So who is doing that? Who is collecting all flexibility services? Aggregator, flexibility aggregator, right? Is flexibility aggregator profit seeker?
Should not be.
So what does aggregator do? Aggregator? It's TSO.
It collects smaller resources.
Is any of one working with aggregators in your PhD projects? Yeah? Okay, what does aggregators do?
It just pulls out of little flexibility
Very good.
services together in order to be comparable for conventional generator and trying to produce and give products in the market.
Good. What kind of game they are playing? Like the games that we played in our childhood. Tetris game. There are small pieces of flexibility that they can get from heat pumps, I don't know, from others, from EVs, from thermostatically controlled loads, and then they put these small pieces together to build what? A big amount of flexibility services, but in different forms. FCR, MFRR mostly, right? They are trying to do that. Good. So aggregator is a profit seeker. So tries to gather all small pieces of flexibility together and sell them mostly to TSOs, right? Good. I think this is my last slide in this stage. Why energy communities? Again, the half of the posters, or maybe not half, 30% of posters that you presented, they were about energy communities or local energy markets. Why do we need them? That's my first question. Second, why do we need TSO, DSO coordination? So I like that you talk for 5 minutes in your groups and tell me some reasons. Why energy communities? Why do we need that? Why we have EU directive about that? And then, okay, TSO, DSO coordination. I didn't talk much about that, but also you can talk also about that. You have 5 minutes. And then a break. Let's now find answers together. Okay, I drew a very beautiful energy community for you. Sorry, I'm not very proud of my drawing skills. Let's say that we have energy community. For example, they are in the same neighborhood. For example, they are all, think of DTU campus or also buildings close by DTU. So all of them, they are in the same location. We will extend that later, but assume that location-wise they are close together. And all of them together, they are connected to the distribution grid using a single, I don't know, interface or whatnot. So all of them, okay, we have, let's say, a number of consumers or even prosumers. Maybe some of them, they have local production. Maybe some of them, they have a small storage. Or maybe one of them has heat pump. Some of them, they have EVs, right? So why are we interested in building energy communities? Different reasons, at least 2 reasons. What's that? Angel, first.
In that way, you incentive people to have renewable energy sources and distribute the energy sources, not to, for example, avoid or delay investment in the grid.
So you are saying that you incentivize them to share renewables with you. Yeah. How do you do that?
Because in a local energy community, you reduce the amount they pay for the energy. If they build have their own rooftop PV.
No, I agree. But how? First of all, why are you interested to incentivize them to trade locally? Yeah, Thomas?
Less need for transporting electricity. So
for who? Who is happy here?
TSO.
TSO mostly, but DSO. Who is DSO? Distribution system company. Distribution system operator, right? DSO and TSO, and they are totally separate entities, right? So DSO is happy to make sure that DSO in 5 years, 10 years, next year is not going to reinforce the grid, right? Okay. So for that, DSO prefers to make sure that people, they are going to trade locally. How DSO can do that? How DSO can incentivize people to locally trade?
Dynamic pricing.
Pardon me?
Dynamic pricing.
Very good. Dynamic tariffs. Very good. What, can you tell a bit more, Nick? What's going on in Europe? That's, again, very nice PhD topic. Dynamic tariffs. Why? What's that?
So price depends on the total load of the community.
Uh-huh.
So like what Florence is doing.
Good. Have you checked your electricity bills? What are the ingredients? What are you paying for? Pardon me? If you check your electricity bills, there are three things. What are they? Yeah?
Energy, tariffs, and taxes.
Okay, tax, I put it here. We are not playing with that. Okay, it's sensitive.
And grid cost?
Grid cost. What is grid cost? So the cost to have access to network, even if you consume or not, you have to pay that. It's like subscription. You are using infrastructure, right?
How does the grid cost compare to energy costs?
Yeah, I'm going to put that. And the first one is energy cost. It's based on how much you're consuming, right? Okay. Energy cost, it could be, I don't know, a fixed, I mean, it depends which retailer. You are paying energy cost to who? To retailer, not DSO. You are paying to your retailer, the one who provides energy to you, right? Okay. And me in my house, I have option to choose between retailers, and they may offer me different pricing schemes, right? So retailer by retailer, it might be different. But grid cost, to whom are you paying? DSO. And what we call them is, it's dynamic tariffs. Sorry, it's tariffs. Right now it's static. What does it mean? Okay, if it's flat for all hours. Okay, now DSOs are happy and make them non-flat. So for example, in peak hours, you are paying more for tariffs. You can say it's dynamic in time. But now DSOs, they are pushing towards more dynamic in terms of what? Also, to differentiate people in terms of their location. They are going a bit towards US markets. It's a negotiation between regulators, DSOs. Is it legal or not? It's still a debate. So the regulators, they are pushing towards local markets. DSO says, no, dynamic tariffs is easier solution. We like that, right? So if you talk with DSOs, with retailers, you see that there's ongoing debate between local markets and dynamic tariffs. Okay, grid cost. Back to energy community. How DSO, not retailer, can incentivize people to build energy community? Grid tariffs. Okay, so what DSO can say to energy community?
If you consume the electricity you produce locally, you will pay less.
Exactly. So DSO can say to the community, the community has a nonprofit operator, and DSO can say that if you promise me your consumption in the interface will not go beyond 10 kilowatt, 100 kilowatt, whatever, you can have a reduced tariffs, right? But how to handle it, how to make sure that the consumption will not go above that threshold, it's your job. So then you need to trade locally, right? Okay, that's one thing, one idea, one reason to have energy community. So as we talk, how energy community can build local tariffs. It's a very interesting topic. You need to have very advanced game theory knowledge, and I think it's a very nice topic to work on. It's very timely. But what's the second reason? So now energy communities, they also like to earn money. By reducing grid tariffs, they save. Now they like to earn. What kind of products they can produce? Flexibility services. What type of flexibility services? FCR and MFRR, mostly FCR, because usually they are fast enough. Good. So now community can earn money. Let's say that they play like Tetris game, as I said to you. They can generate FCR, and they can sell it. Then they earn $100 in a time period. So who is going to receive that $100?
All members.
So who is it? It's energy community. Okay, we have 100 prosumers. Who is receiving that? Now it's a cooperative game. Shapley value, blah, blah, blah. You can think, okay, how now I can redistribute $100 among prosumers? Or you can build a local competitive market. And it will be computationally way less expensive, right? To have non-cooperative games set up rather than cooperative one, computationally. But without market power, you can see that the results are the same. I can point you to papers to read about that. Where is the aggregator here?
Local market operator.
But operator doesn't earn money here.
I mean, there is already some debates going on about that. But
Does real aggregators these days in Europe, Germany, or other, do they like energy community? No. You are kicking out aggregators if you build energy communities. You are going to have aggregators, but non-profit, right? By energy communities, you allow people to sell their own products directly in the market. So you are trying to remove profit seeker or profit maximizer aggregators. Okay, so my last things before break. Sorry. Okay, so far when I say flexibility services, you tell me FCR, MFRR, AFRR, but is it the only things? Or can you provide something more? I mean, your retailer will do. Energy community will not do that. There is still a retailer who is supplying energy community. That's the retailer participating in the day-ahead market through a BRP again. Yeah?
You can have the
TSO. You are selling FCR, blah, blah, to TSO, to stabilize frequency. But DSO may also need services. What kind of services? Yeah. There might be some congestion, something here. So you may need local services. Who may need that? DSO. Still, that's another amazing PhD topic. How to design local markets for DSO. And before that, what kind of services we have to produce? We have to define for DSOs. DSOs need these services for congestion management, for resolving voltage issues, blah, blah. Should it be like FCR, MFRR? No. They are not about frequency. But when you go and talk to DSOs, they say, I'm not interested in running a market, right? So it's a big problem. How to convince DSOs that you need a market. They see everything, every solution, dynamic tariffs. You go with DSOs, they talk dynamic tariffs, right? Is it the right way, or do we need to convince DSOs we need local markets? And if so, what kind of products? And if so, how we are going to clear that? How are we going to price it? What DSOs they are clearly saying today is that we are not going to clear market every day. Maybe once per month, we can work with that, but not every day, not like TSOs. The last topic before break. The second one was TSO-DSO coordination. That's a huge topic. We can have 20 PhDs about that. Why do we need that? Could you just speak up a bit? Uh-huh.
But when the TSO is trying to provide this flexibility, it might violate that operation.
Very good, very good. Any extra? Any addition? Okay, my question. Why do we need coordination between TSO like Energinet and DSO like Radius in Copenhagen? They are totally different entities. They talk to each other, but they are different companies. They have different business models, different CEOs, whatever. Why do we need coordination between them?
Selling the same product.
Pardon me?
They're selling the same product.
No, They have the same product. No. No. They are running. They don't have any product. TSO runs transmission system. TSO runs distribution system. They don't produce anything.
No, I mean the congestion in one of these networks affect the other one.
No, transmission system tries to resolve congestion. Transmission area, TSO tries to resolve congestion in the distribution. They don't need to talk to each other much. They, yeah, please.
TSO's requirement might adversely affect the DSO's network if the flexibility is procured from the...
Okay, I need a bit more obvious reason than that. I buy what you're saying, yeah?
The whole paradigm of distribution networks is changing. So there are more sources at distribution level
Okay.
than previous transmission levels. And
Yeah.
distribution networks are not only used for distributing the electricity to end users, they're now more active.
Yeah, it's almost. I agree. Let me help a bit. So TSO comes and buy FCR or MFRR from this energy community. This energy community is connected to where? To TSO's domain, to distribution grid. Now TSO needs to activate FCR or MFRR. And TSO activates that. So energy community starts consuming more or less without having who in the loop? DSO. DSO is not aware of anything. And suddenly DSO may realize, oh my God, my constraints, my local constraints are being violated, right? So, the problem is that the big sources of ancillary services in future will be in the distribution system. Who is going to activate that? TSO. And here DSO will say, oh, come on. This might be dangerous for my system. You have to talk me before, and then I can see which resource you can activate. Or even it should be more active. Before energy communities, others going and participating in ancillary service markets, they have to get a green light from who? From DSO. So there are a lot of topics, how to create this coordination between DSOs and TSOs. Some people, for example, they are thinking of joint ancillary services, but it's not going to be a solution because the type of ancillary services TSO and DSO needs, they are different. One needs for frequency, the other needs for local, I don't know, congestion issues or whatever. So I'm not sure still today we have a concrete solution how to create a coordination between TSOs and DSOs, right? Very good. Let's have a 15 minutes break and well, I'm not sure we will reach to part 3. That's the most fun part. But part 2, you will see more equations. Thank you. Let's have 15 minutes break. Okay. Yeah, part 1 took longer than what I expected, but it's fine. To be honest, I prefer to have kind of a bit inspiring talk rather than presenting a single paper. So I hope when you leave today, this lecture, you have a better idea, and when you think of your topic, PhD topic, you say, okay, maybe here I need to think a bit more. So maybe here I need to explore things a bit more. So if it happens, I'll feel very happy. So in the part 2, I will mostly talk about, sorry, let me activate pen. Yeah, I'll talk mostly about market design, and in part 3, I knew that part 3 I will not be able to cover everything. If you check, there are many number of slides, but I did it intentionally because you can check the slides later on, but I'll not be able to cover everything in part 3. So part 2 will be more about the basics of market design, something that you have to be very careful when you say I'm designing a market for electricity, for flexibility, for inertia, for FCR, for whatever. There are some common rules, common important things that you have to be very careful when you design a market. Or market for something else, market for iPhone, market for laptop, whatever. There are some common things in mechanism design that you have to be careful about that. And in part 3, hopefully, I'll try to cover the integrated part. Okay? Good. These are the three Bibles of the electricity markets, right? Especially the paper by Schweppe et al. In 1985. That's the main book that, based on that, electricity markets in the US mainly, they were developed. So if you are working on electricity markets, you have to have that book in your library, right? Good. Let me start with the simplest example that you could think of. No network, two generators, G1 and G2, and two demands, both elastic to price, D1 and D2. G1 is cheaper, has 100% megawatt capacity, and the offer price representing her cost is $12 per megawatt hour. G2 is a bit more expensive, $20 with a capacity of 80, and two demands, both elastic to price. One likes to buy max 100 megawatt, the other one max 50 megawatt. D1 is willing to pay max $40 per megawatt hour, while D2 is willing to pay max 35. So if you like to clear it by heart as a market operator, what will be the schedules of G1, G2, D1, D2? Okay, the demands will be fully supplied, so the total demand will be 150, and in the generation side, G1 will produce 100 because it's cheaper. G2 will produce the remaining 50. What's the price? We have different proposals here. Who says 20? The rest says what? There are people saying between 20 and 35. Who thinks that? No, it's 20. If you check KKTs, you will see the only solution that admits the solution is $20. Not, it's unique. The multiplicity only happens when your demand, if you increase or decrease your demand, you are changing the generator. Then the price multiplicity happens. But here it will not happen. Here is the last generator dispatched. It sets the price. It's 20. If you like to check, it's something nice. You derive the KKTs and see with what dual variable admits the solution. Okay. Good. So I said wrong here. It's 20. I have to correct it. Good. If you like to clear the market using optimization, that's the optimization. So what do we try to do with this optimization? We are trying to maximize social welfare. Constraint to what? Constrained by production limits, consumption limits, and power balance equality, right? I start from here because at the end of this part 2, I like to end up the properties in market design that you have to be very careful about, right? So that's why we are starting with this simple example. That's the goal. Okay, so we are trying to maximize social welfare, which is the utility of demands minus the cost of generators. And then we have consumption limits, generation limits, and power balance equality. And here there is a no network. What is the lambda? It's dual variable. If you use uniform pricing, it gives you what? The price. Okay, very fast question. What is the dual variable? Price. I know, mathematically. Here you define lambda to be your price. But what is dual variable if you talk with a mathematician?
The sensitivity of the Lagrangian with respect to the generation.
Oh, very good. Sensitivity of here, objective function.
The Lagrangian, or
on right hand.
Yeah. Okay. Also, you can also say about baseline Lagrangians, but simply you can say sensitivity of objective function, the value of objective function with respect to any perturbation, any small change in that corresponding constraint at optimal point, right? And you can check the sensitivity right-hand side and left-hand side. You have to check both, not just right-hand side. So this is exactly the case that the prices might be different. If the right-hand sensitivity and left-hand side sensitivity are different, you may have multiple prices. But you have unique price if the left-hand, right-hand side sensitivities, they are exactly the same. Good. So, again, as I said, I like to reach the point which properties are important, right? So, so here we have 4 participants, 2 generators, 2 demands. How can you make sure that they are happy with market outcomes? You said G1 will produce 100, G2 will produce 50, the price will be 20. You disseminate that. Nord Pool disseminate the outcomes at 2 p.m. How to make sure that everyone is happy? Or do you at all care that people are happy? Right? You are going to design a market. Do you care about people that are happy with your market outcomes? Are you? You should. Otherwise, people will deviate. They will always be able to find a reason to deviate if they are not happy. It happened a lot in Kaizo. Joe maybe can tell us.
I can't.
Right? So if you don't sure that people are unhappy, if people are unhappy, definitely they will find to justify why they are deviating from market. They can say, I don't know, there is a failure or something like that. So you need to make sure that people are happy with market outcomes. How do you know that people are happy?
Maybe given the price, the optimization problem for each generator yields to the optimal solution.
Fantastic. Fantastic. You have to make sure. This is the price I'm paying, that $20 per megawatt hour. If they optimize internally, if their solution is different than market outcome, they will definitely deviate. Right? At least in the long run, they will deviate. Okay, very good. So, Ogun, you said something good, so I'm passing this. So, this is what Ogun said. What's that, Ogun?
So this is the profit maximization problem for each generator.
Okay, and what's the variable?
The variable is the internal power dispatch level.
Okay, and what's the lambda?
The lambda is the announced the system lambda.
Is the lambda variable for generator?
No.
No. So we are trying to see for fixed lambda, what will be the best, the profit maximizer scheduled for generator G1. Do you agree? So what is the objective function? P production times lambda price minus the cost. So it's the profit, right? And the only internal constraint is the limit, is the capacity limit. You agree? Okay. So can you think of the same for generator G2? And you can think of the same from demand side. What does demand try to do? Maximize what? Utility or surplus. What's the surplus for demand? You remember, if we have the demand and supply curve and you find the intersection, so whatever we have above price between the 2 areas is the surplus for consumers. So here, she is buying PD1. 40 is the value of electricity for her, and lambda is what she's going to pay. So 40 minus lambda times P is the value of electricity for demand. It's the surplus, right? So this is for D1 and D2. Are we missing something compared to optimization problem? Power balance. Okay, now we have power balance. Okay, now we have 5 pieces. The 4 first boxes, they are optimization. The last one is a constraint. Can you give me a mathematical trick to also make it optimization? Okay, maybe, I like to get lambda also. Pardon me? Yeah. No, I don't like to have a dummy objective saying maximize one subject to this.
For
Tell me something that also lambda is a part of the play. Okay, derive an optimization, or develop an optimization. Whose KKT is this?
Lambda times.
Very good. Exactly. Very good. You can have that. Minimize over lambda, and then in that object optimization problem, which has it's an unconstrained optimization, lambda is the variable times the power balance equality. So if you derive KKT, what will be your KKT? You derive the stationary condition, which is the derivative of Lagrangian, and Lagrangian here is exactly the same of objective function because you don't have any constraint. So with respect to lambda, so it will be exactly the power balance equality. You accept? You buy it? Good, thank you. Good, now we have these 5 optimization problems. And the last one, I call it price setter. I didn't. Actually, Arrow and Dibru, they did. In 1952, they called it a fictitious player called price setter. Actually, they called it something else. But let's call it price setter. I don't remember what they called. But now we have 5 optimization problems, right? Each representing one agent. Can we solve them separately? Who says yes? Who says no? Who says no? Who says yes? The others are neutral. You don't care about solving that. Why do you ask that? Why can't we solve them separately? Who is saying that, Nick?
They have common resource. They have lambda in all of them.
Yeah, in G1, G2, D1, D2, you have lambda as what? As variable or parameter?
Parameter.
Thank you. In the last one, price setter, lambda is a variable or parameter?
Variable.
Variable. Okay, in price setter, the 4 variables, D1, D2, G1, G2, are they variables or parameters?
Parameter.
In the other 4, they are variables or parameters?
Variable.
Can you solve them separately?
No.
Thank you. No, can't. We can't solve them separately. So what to do? Pardon me? It's what? Iterate. Okay, now you have a market clearing problem, Angel, in Spain. 10,000 participants. Solve it iteratively. That's your task. You're working with, in Malaga, right?
Yeah.
With Miguel Press. Okay, I'll write him that, okay, Angel have a different idea. Solving it iteratively. Okay, something non-iterative. Sergio taught what? KKTs. Okay, you can replace the optimization by the KKTs. Then what happens?
You have a system of equations.
Then if you replace each optimization with KKTs, then you can collect all KKTs and solve all at once. Then you will have what? Carlos? A price of what? Sorry, a system of? A system of equations, right? Whatever, it's a system of equations. And then you can solve all KKTs at once. That's how you can. What do we call this? This is equilibrium problem. It's a game theoretic problem. Is it a cooperative game or non-cooperative game? Non-cooperative game. Everyone tries to maximize her own payoff. True? Good. Oops. Okay, we need to solve all of them together. This is a game theoretic problem. And in economics, it's called competitive equilibrium. Do you know when this problem has been invented? Any idea?
A long time ago.
Long time ago. Yeah. It was Kantrovich in 1939. It's the first one, I think. He talked about that competitive equilibrium. And then it was Paul Samuelson in 1952, I guess. And then Arrow Dibru. They are very famous people. They worked on that. All of them, they got Nobel Prize. If you like to learn more about all these things, there are wonderful 2 books you can go and read. Also some other resources. Okay. This is John Nash. Have you watched Beautiful Mind? Okay, there it is. Good. What John Nash did in 1950 something, and also he got Nobel Prize for that. John Nash said, or explained, under which circumstances what happens. There is a solution for our equilibrium problem. And what does it mean, solution for equilibrium? When we say we have a solution for equilibrium, it means that in that solution what happens? No one can increase its profit, payoff, whatever, by deviating unilaterally from the equilibrium solution. We find the equilibrium solution. If you solve it alone, maybe you can have a better profit, but we all solve together. And that's a point that I say, okay, if I deviate, I will not gain. We are all stuck there. That's equilibrium point. And we call it Nash equilibrium point. Okay? And John Nash proved under which circumstances we have that condition. Good. I told you a bit about, in recap for Sergio's, after Sergio's talk. Again, remember, I like to talk to you about what important things you need to care about when you design market. You remember I talked about pure Nash and generalized Nash, huh? Is it pure Nash or generalized? This is generalized? What is the pure Nash? What is the pure game? Pure Nash equilibrium problem.
They don't have constraints like common.
Make it general, not just common. We are not necessarily talking about common constraints. So in pure Nash game, what you have? Only objective functions depend on the strategy, the decisions of others. Our feasibility set, our constraints are totally internal. It's independent of others. What is the case in generalized Nash game? In GNE? Not only objective function, but also our constraints depend on others. What's the case here? Do you see any constraint that depends on others? Pardon me? Yeah, the price setter one? Is there a constraint there? It's only objective function. That's why we tricked that. We invented that to put others' decisions in the objective function, not in the constraints. So someone said put, I don't know, what's that? Fictitious objective function like maximize 1, 2, whatever, subject to this. No, then we made it GNE. We don't like it. So, conclusion, is this pure or generalized? Pure. We like it. Why? Because when you design a market, it should come from an equilibrium problem. If you like to have a good market, make it pure Nash. Why? Because you can easily prove under which circumstances a solution exists, and the solution is unique. Do you like to have a market with multiple solutions? No. Then people will complain why you choose solution 1 rather 2. In number 2, in solution rather number 2, I gain more profit. Why you choose number 1? We like to have a market with a unique solution. That's critical. So when you design a market for inertia, whatever, think of uniqueness. Right? That's one important takeaway. To that, you need to have, hopefully, pure Nash game. Good. I like to be fast here. Okay. You saw that now we have an equilibrium problem. Everyone maximize their own profit, whatever. Also, we have a price setter optimization problem. Also, in the beginning, I saw that we can have optimization problem, that we are maximizing profit. That's one optimization problem. While in equilibrium, we have a set of optimizations that they are linked. You are designing a market. Which one you prefer? Are they the same or not? Who says they are the same? you are designing a market. You have two choices. You can develop optimization problem, the one in the right. You maximize social welfare subject to all constraints, including consumption limits, production limits, power balance. That's one choice, choice number one. We call it optimization choice. When we clear day-ahead market, whatever, everywhere, we are solving that. The other one is equilibrium. With that, we sure that everyone is happy because we are going to find a Nash equilibrium point. Everyone tries to maximize their own payoff, including price setter. Now you are the one consulting Nord Pool. And Nord Pool asks you, okay, I'd like to clear the market. How should I do that? Are you suggesting the equilibrium choice or optimization choice? But how do you know that people will be happy? With equilibrium, you know. With optimization, how do you know?
The KKT for both problems should be very similar.
Very similar. You have to show that they are equivalent. If equilibrium is the same as optimization, then you know that at the same time that you maximize social welfare, your solution will be Nash. Equilibrium point means that everyone is happy. Or no one can deviate from the market outcomes. Otherwise, your market will collapse. Is it happening that in Australia? Right? One of the big blackouts in California, in CAISO, in 2001, something like that, it happened because of that. Some people, they found a way to manipulate the market and deviate. And eventually that happened. Go and read about this story. It's very interesting. Okay, you have two problems. Guys, you are mathematicians. How to show that they are equivalent? Now you said derive KKTs. If you have two systems, whatever, two optimizations, two equilibriums, one optimization, one equilibrium, whatever, derive KKTs, compare. If they are the same, the problems are the same, are identical. Okay? I'm not going to go that part, but here you can read the slides later on. You can derive KKTs, for example, in the example. This is the KKTs in the equilibrium problem. If you can calculate, if you put all KKTs together, you will have MCP, mixed complementarity program. It's a system of equations. How can you solve that, by the way? You have a system of equations. How do you solve it? And it's nonlinear because you have complementarities. How do you solve it? Remember from Tuesday? Pardon me? You can go with monotone inclusion trick. You can make it monotone, and you can solve it iteratively, right? But we don't do that. We use solvers, because those solvers do that for us. We don't care what they do in behind, right? But this is what they do. Which solver we use? Path, for example. I don't know if there are other solvers, to be honest, or not, but Path is the more typical solver you use for MCPs. Or we ask Sergio to come and write a program, a code for us, and we do that. Good. And if you also solve derive the KKTs of the centralized optimization, you will see they are exactly the same, right? So when you clear the market, you can write it as an optimization problem, maximizing social welfare. Do that. It's easy. You can solve easy LP solvers. Groby, Stiplex, many other. Or you can do, what is the simplest LP algorithm to solve? That you can do it by hand? Simplex. You can use Simplex and solve it and find the bounds, right? You don't need to solve MCP. But the good thing, the beauty is that this is equivalent to an equilibrium, so no one will deviate. We love it. So you like to design a market for anything, make sure that there is an equilibrium behind. Make sure that ideally there is a single unique solution for that. Otherwise, you will not be able to convince people why you choose one solution rather than the other one. Right? Very good. Now I added network here. So can you tell me what these three constraints are? It's not like zonal setup. It's more like nodal setup that we use in US, but without unit commitment constraints. What are the last three constraints?
DC power flow.
DC power flow. Great. So we have dual variable lambda n, one price per node, LMPs, locational marginal price, right? Okay, now I added network. Do we have an equilibrium for this?
Depends on the congestion. If you don't reach any limits, that's fine, right?
No, my question is this. This is an optimization problem, network-aware optimization problem. We clear market with that. We like to know if there is an equivalent equilibrium for that. Do we have? In my previous example, we didn't have a network. So we saw that we have equilibrium problem. Everyone tries to maximize their own profit. And also we have optimization problem for the price setting. Now here I added network. Do we still have an equilibrium problem? Equivalent equilibrium problem?
Without congestion, yes.
We don't know. You first clear market, and then you realize there is a congestion or not. You don't know a priori. So my question is not conditional. Question is, do we have an equilibrium problem equivalent to this optimization problem? Yes. Where do you put network constraints in your equilibrium problem? Price setter. Okay. Any other proposal? Price setter sets the price. It's on the name. Price setter doesn't care about network constraints. What should we do?
We need to have another optimizer.
Oh, we need what?
Another optimizer for that.
Another optimizer. Who is the another optimizer?
Network.
Transmission, system,
Operator.
owner, operator, whatever. Okay. In Chile, we have it, right? TSOs, they are transmission system owners. They are profit maximizers.
Yeah, but they have a, no.
You have it. So if you invest in transmission systems, do you care about profit? Do you have a source of profit?
Yes.
What is your source of profit? Pardon me? Grid fee something are out of the market. Let's talk about the market. Let's talk about the full librarized market. Pardon me? Sorry, I can't hear you. Oh, congestion rate. Now I got it. Yes. What's that?
So it means we invest online and we collect this the congestion rent, and sometimes the transmission company will receive an incentive fee from the regulator or something.
We have two buses, N1, N2, and you have only one line. Price here is lambda N1. Price here is lambda N2. And the flow is F. Let's say F. So what's the profit for transmission system owner here? Pardon me? The difference between prices, okay. Which prices? Lambda 1 minus lambda 2 or lambda 2 minus lambda 1? Depends. The direction of flow from N1 to N2. So what is your profit? So Martina suggests lambda N2 minus lambda N1. That's it, or something more? Times flow. So you call it congestion rent. What does it mean? Transmission system owner is simply what? A trader. Arbitrager. But a spatial arbitrager rather than temporal. So battery arbitrage over times. Transmission system operator does arbitrage over the space. So here, the transmission system operator buys power F at price lambda N1 and then sells it back at node N2 at price lambda N2. And if the prices are different, then the transmission system owner will earn something. But if the prices are the same, There is no profit. So when under which condition those prices are different? Congestion. And if there is a congestion and flow is from N1 to N2, which price is higher? N2, lambda N2. So does transmission system operator like congestion? Merchant wants, yes. Yes. Good. So let me go for the optimization problem. So now we have this box. So each generator maximizes the profit, each demand maximizes the surplus. We have price setter, one per node. But now we have a new box. Said, you said we need a new optimizer. Yes, we need. This is the one. So who is it's representing transmission system operator. Maximizing what? Congestion rate, subject to transmission capacity. Right? Okay, I like to be a bit fast here. Okay. But we really don't like to have a transmission system operators who are trying to earn money based on congestion rents. It looks a bit weird. We like to facilitate the network, whatever. So in Europe and US, again, we have different concepts. In Europe, yeah, transmission system operators like Energinet or others. First of all, there is a zonal setup. So the only congestion rents that happens is between the zones, because within the zones there is no transmission. So your congestion rent only comes from the capacity between the zones. And actually they collect the congestion rents, and I don't know, every quarter, something like that, they proportionally split congestion rent among the TSOs, like Energinet. And then Energinet use that for grid expansion or lowers the grid tariffs. That's how we do in Europe. But in US, there's a different story. What's that? FDRs. So you have to read papers by Hong Pu Chao, by Bill Hogan, others in 1990 or 85, something like that. What is FDR? Financial transmission rights. Let's say that we have a generator here, a demand here. So we have a flow something like that, right? And then here the price is, let's say, lambda 2. Here the price is lambda 1. And the flow is F. And let's say that this is congested now. So we are going to have a congestion rent of lambda 1 minus lambda 2 times F. This is what the transmission system owner gains. So what is FTR? Okay, financial transmission rights. Financial rights. Good. Who is selling those rights? The TSOs, the transmission system owner. So every year, every 2 years, every quarter, depends on the transmission system owner, there is an auction for FDRs. Who are the buyers of FDRs? Who is the buyer in this example? Who is potential to buy FDR? So okay, let me explain like that. So when you buy, for example, 50% of the right of that line, it says that whenever there is congestion rent, if I buy 50% of FDR, whatever you earn as congestion rent, 50% of that is mine. That's the simplest definition of FDR. There are also other points, but this is point to point. So let's say that there is a person or agent here that can buy, for example, 100% of the FDRs, right? So a priori, beginning of the year, someone, either generator or demand, comes and buy this right from the transmission system owner in an auction. And then whatever we collect as congestion rent will go to that right owner. Who has the incentive to buy the right here? Demand or generator? Demand. So if demand buys FDR, though is paying lambda 1, which is a higher price, but if we pay back this congestion rent to demand, at the end of the day, its demand is paying lambda 2. So we are hedging the demand. We are hedging the risk of demand to paying a higher price. Is it clear? This is financial, right? So I told you that the transmission system owner, at the end of the day, is an arbitrator, a spatial arbitrator. We can also think of a temporal arbitrator, which is who? Storage. Can we think of financial storage rights? Yes. So read papers of Eliam Bitar, Josh Taylor, et al. It's about, also we have something similar for temporal arbitrators, for financial storage right. What about physical rights? Can you differentiate between financial rights and physical rights? How, Nick? I have an asset, this. It's useful in power system. I can sell financial right and physical rights to you, Nick. If I sell financial rights to you, what does it mean? If I sell physical rights to you, what does it mean?
This unit generates profit and owe some part of it.
Very good. That's the financial. In the financial part, this asset is being used by the market operator system. It's not me. It's not the right holder who schedules that. It's the system operator schedules this asset, uses this asset for the sake of the whole system, for social welfare maximization. And if we get any profit out of that, the right holder will get the share. But what is the physical right?
This is what the system operator gets?
Not anymore. It's the right holder who decides about the schedule, the use of this asset. For example, if this is a battery, Nick says that I have 50% physical right. I decide to use this 50% like this at the next hour. So you schedule the asset, you rent the asset, and use it as you wish. But to get the right, the physical right for the asset, you have to compete with others, right? So one potential PhD topic, right, is, yes, please, Mert.
Do you have to use the entire capacity if I get it? Is it a mandatory or?
No. Just you are booking the capacity. Okay, you can also think of financial flexibility right and physical flexibility rights. I can convince you maybe offline that's a very good idea, right? If you have some flexibility assets in the system and you don't like to go and every day participate in FCR markets, MFRR markets, whatever, you can give the right to others. You can give the right to aggregators, whatever, and then they can use their benefit. And then you will be paid a priori in an auction. So if you are interested, I can convince you, hopefully afterwards. Good. There are some exercises that I put, you can check it out later, after the class. I usually ask my students to solve them. So one question, for example, is how to solve equilibrium problem iteratively. So you need to learn something about Walrasian auction. Then the other exercise is that you have an equilibrium problem. How to find that, how to know that there is an equivalent optimization for that. Let's say you design a market, you start with an equilibrium problem. Okay, it's good. But now I need to find an equivalent optimization for that. And it's not easy to find. How to know that, whether there is an equivalent optimization for that or not. Then you need to derive the game map. You need to derive the Jacobian matrix, or Jacobian matrix. And then you have to check the principle of symmetry, if that matrix is symmetric or not, right? I put some guidance here, so hopefully they will help you. And then, how to know that I have a unique solution. First, there is a solution exists, and how to know that the solution for my optimization problem for my market is unique. Then again, it's based on your Jacobian matrix. You have to check and see if it's positive definite or not. If it is, you are happy. You have a unique solution. If not, you don't know. Then you have to go and use other techniques. Maybe you need to learn about degree theory or something like that. Good. Okay. So remember, whatever market you design, so far you will learn that there should be an equilibrium for that. The solution is ideally, a solution it should exist. Otherwise, well, you are screwed. Hopefully the solution of your market is unique. These are the most important things. But on top, you need more properties. So remember, for example, Pierre on Wednesday talked about data market. And then he said, this is the properties I have. Why Pierre used linear regression? Why he didn't use, I don't know, neural networks or something like that? Why? Because neural network or whatever, they are nonlinear operators, and at the end of the day, you cannot prove good properties for your market. Or why he used Shapley? Because it's linear, and you can show that you have desirable properties. Otherwise, if you use some, I don't know, crazy methods, then you may not prove that you have good desirable properties for your market. So whenever you say, I like to design a market, the first question that we will ask, or you will be asked, is, okay, what market properties you guarantee? Clear? The very important fundamental properties in mechanism design is this four: efficiency, incentive compatibility, cost recovery, and revenue adequacy. I like to be fast here. What is efficiency? How to know that my market is efficient? Everyone is happy. And at the same time, you are maximizing social welfare. That's the most fundamental thing. What is incentive compatibility? There's incentive for people to be truthful, to bid their true bids or true costs or utilities. What is cost recovery? Yeah, making sure that your profit will be minimum zero, so you will not end up in a negative profit. And what is revenue adequacy? And in a special case, budget balance. Pardon me? What is positive?
The money that the system operator recover from demand and then basically...
Yeah, system operator, you are the system operator, should not end up in a negative profit. And in the base case, what you earn is what you collect is the same as what you are going to pay people, right? Okay, it's very common that we use LMP-based markets, right? Based on dual variables. First of all, there is something called impossibility theory. What does it mean? Have you heard of impossibility theory? Yeah, unfortunately, there is a conflict of interest between these four properties. You cannot have all of them at once. So as a market designer, you have to decide which property you like to pick and which one you like to give up. No way to have all of them at once. That's bad news. So, yeah, so you can read about impossibility theory here. So, uniform pricing, those with dual variables. Do you know which properties you have, which properties you gave up? Efficiency. Is everyone happy? Yeah, I agree. Incentive compatibility. Is there any chance for people to lie and behave strategically and bid at a higher price? Yeah, whatever. Yes. Yes. With uniform pricing, people, they can lie. They can behave strategically. Then you can say that, okay, then if people behave strategically, then it means that social welfare is being compromised. So also in that sense, we are not efficient. But people are happy, but for given bids that might be strategic. For given bids, people are happy. But it doesn't mean that social welfare is maximized, because people, they are not necessarily truthful. But why do we like that? Why uniform pricing is very common? Because we have cost recovery and revenue adequacy. And actually in my course, I ask people to sit and mathematically prove why uniform pricing is guarantee revenue adequacy and cost recovery. And how to do that, you can learn the guide, but you need to know how to derive the dual optimization, and so forth. Okay?
Very quick question, but
Yeah.
you have the cost recovery for the optimization problem that you described, right? Because in case of unit commitment, I think as we described, there's no
Okay, very good question. Okay. Yeah, I eliminated that part from my slide, but I can't. Yeah. In the optimization problem that I showed you, there was no unit commitment problem. I cheated. And then I said that in this optimization problem, we had cost recovery and revenue adequacy. Yoo-hoo. But when you add unit commitment constraint, as we talked, when you fix binaries, then startup cost, fixed cost, they are all being removed, and the price, uniform price, doesn't reflect them. Then again, the cost recovery is gone. So uniform pricing, if you think it's not that amazing mechanism, but we don't have any other option. We have VCG, Vickery-Clark, Groove, the three genius gentlemen who also got Nobel Prize, and also they proved something which is incentive compatible, which is efficient, but not revenue adequate, right? But electricity markets decided to not use VCG yet. Maybe they will use. Good, this is end of my part 2. I have half an hour for part 3. Any question? And I suppose, Yannick, also you need 10 minutes of my time, right? Can you do it at 12, not steal my time? Good. I think Yannick is going to disseminate some feedback forms, so we will appreciate that you provide some feedback to us. But let's do that at 12, so I need half an hour to have, right? Good. Do you like to have 5-minute breaks, or are you ready to be bombarded by another topic? Break? Can we agree on 5 minutes, please? 5 minutes, please. Good. Part 3. This is the most applied part with less basics or fundamentals. 130 slides, 20 minutes left, so obviously it will not work out. But I knew that, but I put the slides there because you can read them offline, and hopefully it will trigger your mind to have some idea, something, so hopefully. So here in 20 minutes, I tried to just focus on the most important parts, which is about integrated energy systems. When we say integrated energy systems, what do you think of? For example, different energy sectors, right? Power, natural gas, district heating. Maybe in future we will have system network for hydrogen, who knows? Also now power system is being connected to transportation, right? Also when we talk about integrated energy systems, it's also about coupling sectors. And sectors, they are not necessarily just different energy carriers. For example, TSO and DSO, they are two different sectors, and they are coupled, right? And we need to have coordination between them, as we discussed, right? And why do you think market design could be challenging for integrated energy systems? Do you see any challenge about market design? For example, let's pick one of them, power and gas systems. They are coupled through gas-fired power plants, or power and heat systems. They are coupled through heat pumps, combined heat and power plants, and so forth. So do you see any challenge in terms of market design for them?
Constraints.
Let me first ask, before I question than that, why do we like to couple sectors?
Better optimize them?
Yeah. Very good. We like to couple them and ideally jointly optimize them. Then we can schedule them in an optimal way. Otherwise, if we schedule them differently, there's a very good chance that our allocation is suboptimal. So let's say that we are maximizing social welfare for power, we are maximizing social welfare for gas sector, but it doesn't mean that necessarily we are maximizing social welfare for all together. So co-optimization is always ideal, right? But why don't we do co-optimization? Let's do co-optimization. Does it work?
Sharing information, what the parameters should be.
Yeah. For example, in Denmark, I don't know, we have Nord Pool and Energinet, they are clearing different electricity markets. For gas, also we have market, it's also European market, which is they have a funny way to clear that based on entry-exit methods. But it's totally decoupled on power system. It's a different entity, different sectors, different regulators, they are doing that. Or heat system, we have Varmlast here, clearing heat market in Denmark. We have a heat market, by the way, in Copenhagen. That's very funny. And they work in a very, yeah, I'm being recorded, so I'm not saying something. I'll tell you in lunchtime, but yeah, it's a very funny way. Can we ask them to clear one single market? Theoretically, yes. Practically, no. It will never happen. This is how they work. You ask me why it's happening like that, why Norway has 5 zones, whatever, all historical reasons. They are not going to work together. They are going to work together, but they are not going to merge. So we have to accept that sectors are decoupled, right? And then we think, okay, now we like to design market to increase social welfare, entire social welfare as much as we can. But we have a benchmark. And what is the benchmark? Co-optimization. In our papers, thesis, we can do co-optimization. That's really nice because it's ideal benchmark. Then you know what is the best you can get. But if you go and sell it in practice, I have a very nice market design, let's do it. They will not go for that. But it's nice to have co-optimization. For TSO, DSO, co-optimization. For power gas heat, co-optimization. That's really nice, but it's only being used for as ideal benchmark. Then the next question is that, okay, please respect their independent, or they have independent operators. Now tell me how we can improve the social welfare while respecting they are independent. They are being cleared, for example, sequentially. For example, in Copenhagen, first we have heat market, then they had electricity by Nord Pool, and then gas. Let's respect this sequentiality. Or we have in power system, we have first energy day ahead, and then we have reserve. Oh, sorry, vice versa. So let's accept that and then think, okay, now how we can design a market. And when we are saying about designing a market, it's not just about just designing a new market mechanism. You can also think of other ways, like what? For example, new market products. In Kaizo, they realized that we have problem with ramp. So they created a new market product called what? Flexi ramp. So think of that. Can I have a new market product that help system, that help the two sectors to work better together? That's a nice solution. If you do that, you can save millions of dollars. Or think of new market players. Maybe you can define players at the interface of two sectors. Maybe they can help the total system to function better. And in the not worst case, in a very extreme case, you can think of, okay, let's design the market from the scratch. But it should not be our first choice because it's less likely to be accepted in practice. Am I clear? Good. I'm gonna skip some slides. Okay, new market products, new players. First think of that, and that if they don't work, okay, think of redesigning the markets, but not co-optimization. It will not work out, I think. Okay? Good. I have in the slides some challenges and then some examples for market products, for market players, and how we can redesign market while accepting they are not independent, they are being cleared independently. So definitely I will not be able to go through these 3 solutions, but hopefully the slides are clear enough for you to check them offline, and always you can contact me, right? And come with good ideas. And, but I like to talk about at least the first time in the remaining 14 minutes. Yeah, for example, district heating and electricity systems, as I said, they are connected by CHPs, combined heat and power plants, by heat pumps, by prosumers, right, and others. Yeah. For example, if you have a CHP, heat pump, and heat storage, then you have this feasible operating region. This is the heat production, and this is the electricity production. So in Copenhagen, we first clear heat market. So we say that, okay, the CHPs, heat pumps, whatever, they are going to first produce 150 megawatt heat. First we clear heat market. And then your electricity, in the next stage, you clear power system. This is the range of P min to Mi max that your assets, they can produce power. But they are restricted by your a priori heat dispatch. So if you think of, so when you clear heat market, if you know that, okay, your heat schedule will create restrictions later in the power market, if you would like to be in favor of total social welfare, so instead of clearing heat here, scheduling heat to produce 350, maybe you are going to schedule heat for 150. Why? Because if you schedule heat here, you have less flexibility how much you can produce power later. So there are very nice ideas, for example, how to make heat markets electricity aware, or how to make electricity markets gas aware. For example, there's a very nice paper by the group of Pascal Van Hentenrich, Georgia Tech, saying that, okay, in US, gas market is being cleared after power market. So let's make market power, electricity market to be gas aware in a way that we are maximizing social welfare for power and gas, both at the same time, while keeping those two markets separate, right? Good. So we need coordination between the sectors. And for me, coordination means any mechanism that you respect the sectors are independent, they are working separately, while anyway that you try to increase the information exchange between the sectors in a way that at the end of the day, you increase the total social welfare. If you have that kind of mechanism, you can say that, okay, now I have a coordination mechanism. Am I clear? Oops. For example, yeah, there are some nice papers. For example, between TSO and DSO or whatever, you can think of operational coordination mechanisms. For example, there's a nice paper A says that, okay, first let's make sure that DSO will tell TSO what is the feasible space of DSO in terms of active and reactive power, and then TSO will clear market or whatever afterwards. Okay, that's one way. Or financial instruments. Or there's a very wonderful paper, C, which is not about power, but it's about local information channels. So for example, saying that, okay, we are 50 people here. Every of us, we are maximizing our own optimization. And we have different understanding about, for example, common source of uncertainty. You can prove that if all of us, we have a common understanding of uncertainty, and if we improve our understanding about uncertainty, it's good for the whole social welfare. It doesn't mean that it's necessarily profitable for every single individual. So then the paper C says that, oh, let's think of local information channels. Maybe I don't know, Farad and some others, we can have a local information channel. We share our information to improve our forecast, to improve our understanding, and then it will be good for the whole system, right? Good. I'd like to give you some thoughts for your PhD thesis, and then I'll finish. One big issue when you will like to coordinate system is to understand their physics. Especially when we think of flexibility products, it's very important to understand how the physics of new assets, of our assets we have, like electrolyzers, or how, I don't know, gas is is flowing in the networks or heat. It's very important to have a good modeling of the physics of the system in the market clearing problem. In power systems, we learned about DC power flow. Okay, it works okay. But in gas or in heat, it's not that easy. Even if we do a lot of approximations, for example, in the gas system, the gas flow in networks, if you like to really model the gas flow in the networks, you have to use partial differential equations. You do some approximations, simplifications that Yannick and Erika can tell better than me. And then you will end up to this optimization problem with this constraint. You can think of as like DC approximation, but in the gas. But when we have DC approximation in the power system, it's linear, we are happy. What about this constraint? Is it linear? Is it convex? And I can tell Q is a flow, it's a variable, and PR is pressure, nodal pressures. Is it convex constraint? No. As long as you have nonlinear equality, it's non-convex done. Okay, you did a lot of simplifications and you end up, again, a non-convex model. If you like to understand the physics of the gas and would like to put it in your market model, you're stuck in a non-convex model. And I don't think I need to convince you why we don't like to have a non-convex problem, right? Because of suboptimality, because we cannot interpret the prices with drive or whatever. So you will stuck to other, okay, let's do approximation, let's do relaxation. There are many, many papers about that, about how to approximate this, how to relax this. But still we don't have any concrete rigorous model that we can linearize this constraint called Weymouth equation. So if you are really love applied math and you are full of energy to do something and to impact the society, that's one thing. How to deal with that? We need to have this equation in the market clearing problem for gas.
Can't you just create a machine learning model to replace
Do that. But you have to keep revenue adequacy, cost recovery, transparency, blah, blah, blah. Do that? Yes. I'm not sure.
just to replace the constraint, not the entire optimization problem.
That's nonlinearity. If you do that, the others are linear.
What?
That's the only non-convex constraint.
Yeah.
If you find a solution for that, you are fine for the rest. Right? The last things I like to mention, and then I'm going to conclude, is this. Okay, you told me that we are connecting sectors like power, gas, heat. Why? To get more flexibility, right? So we are getting flexibility from gas sector. How? For example, by stored gas in the pipelines. That we call it line path. Good. Happy. We are getting more flexibility by sector coupling. But is there any challenge? Are we putting, for example, the gas sector in some critical situation? Yeah, right.
You're kind of forcing them to take that option, or
Yeah.
you're kind of binding them to, or you're restricting their view.
Let's say that our power system has a lot of uncertain sources, wind, and now we are connecting our power system to gas sector through gas-fired power plants. And gas-fired power plants are those who are mostly compensate the uncertainty, the variability of wind. So what are you doing?
Adding more uncertainty to gas.
You are propagating uncertainty from power to gas. You are pushing uncertainty from power to gas. And you're saying to gas sector, now it's your job to handle the uncertainty that I'm imposing to you. Right? Is the gas sector ready for that? Are you sure? We don't know. So first of all, the question is that we are getting flexibility from gas sector. Are we paying enough to them? I have to show that the gas sector, they are happy. And second, we need to think of the systemic risk of the entire system. We are propagating uncertainty, but we should do that in a controlled way. We have, so our market design should be aware of uncertainty propagation. We cannot do that as we like. We cannot do it randomly, right? This is the last slide I like to show and finish. This is a paper, not at all about power systems, by Dara Najamoglu. Do you know him? The famous economist at MIT. Have you read the book, Why Nations Fail? Have you heard of that? It's by Dara Najamoglu. He wrote this paper with Asu Azaglar and Alireza Tahbaz about uncertainty propagation or shock propagation in financial networks. Do we have financial networks?
Yeah.
Like banks, financial institutions? How they are connected to each other? By financial obligations, by loans, whatever, right? Then, this is a very practical, fundamental paper published in American Economic Review. That's the top journal in economics. So they say that, okay, we can have shocks in financial networks. For example, one bank may not do a good job, so some shocks happens. I mean, you can think of, I don't know, some shocks to a bank. For example, what happened in 2008. So the very important thing is the topology of our system. So they talked about less connected, let's say ring type connected network for financial network. So every node represents a bank, while the other one is more complete financial network. Let's say that a shock happens to this bank. This bank number 2 realizes or experiences a shock. So this shock definitely will be propagated through the network, right? So the question is that, do we like to have a topology like a ring, less connected, or do we like to have a more complete, more connected network? What do you think?
I think more connected would be less vulnerable to shock.
Okay. Britain doesn't accept.
Less connected.
Less connected to be better?
Yeah. Because then there's the
More connected. Who says more connected? Pardon me?
What would be like in terms of risk only?
In terms of the stability of the system, the whole system, against a shock that it's happening to one bank. Definitely this shock, this uncertainty will be propagated. So in terms of the stability of the whole system, do we like to have more connected system or less connected? So who says less connected? Who says more connected? Who says nothing? And the answer is that both are correct. So here, Daron et al., they show that if the level, the intensity of a shock is below than a threshold, it's good to have more connection because the banks, others, they help each other to damp the shock. But when the shock is above a threshold, then the network works like a tool for propagation. That happens in 2008. One bank failed, then the other bank failed, then the other bank failed, right? So can you think of similar things for energy systems? We are connecting power systems, to gas, to heat, to everything. But this is the proposal that Yannick is also working on that, and Lesia. And I invite all of you, if you like to think of the similar things, and we can work. The topology is important. We have to know how we are coupling systems in terms of uncertainty propagation and in terms of the systemic risk of the whole system. So here we are talking about threshold. Can we find that threshold in energy systems? Let's say that there is an asset in heat system that helps us to improve our systemic risk. How to make sure that that asset is being remunerated enough for the value it has for the system. Otherwise, if we don't define a good market product for that, that asset might leave the market. And then our system will be vulnerable against any kind of uncertainty propagation. Okay? So there are a lot of things in market design that we have to be very careful. And I hope this talk triggered your mind to think about different aspects of market design. Thank you.